Using Wolfram Alpha, we're going to be able to quickly evaluate derivatives, find the derivative function, evaluate the derivative at a specific value for x, which is going to leave us free to focus on applying derivatives to business applications and then interpreting those results. Before we get into that though, we want to look at how we actually use Wolfram Alpha to find derivatives, evaluate those functions. So we'll take a look at a couple of examples briefly here. So in example 1, we want to find the derivative of negative 2x cubed. So again, Wolfram Alpha being very intuitive, we can just tell it essentially what we're looking for, type in that function, and evaluate. And we get the derivative as negative 6x squared. So in addition to that output, it's going to give us a graph of the derivative function, some other things as well. But what we're interested in is that derivative function. So part A asks us to find what the derivative is. Then in part B, we're asked to find f prime of 1. So as a shortcut, I can click on this output, negative 6x squared. Just saves me the trouble of retyping that. It'll automatically put that into our box here. And then I can say evaluate this function negative 6x squared for x equals 1. So again, check that input interpretation just to make sure that comes out correctly. But what we get is that result of negative 6. Nothing terribly complicated that we couldn't probably figure out by hand, but when we get into some more complex functions, that's going to save us some time and energy on our end. So we get the derivative of this function as negative 6x squared negative 6x squared. We get the derivative evaluated at x equals 1 to be negative 6. And then similarly, we could update that phrase that we entered to evaluate it at x equals 2, which should give you a result of negative 24. Evaluate that derivative at 3, should give you a result of negative 54. So I'd encourage you to just go ahead and try those other two examples just to make sure you're able to get those same results. But we're going to move on to looking at example 2, where now we have a slightly more complicated function. So now we want to take the derivative of 10 times the square root of x plus 8. So to get to the square root, I think we could actually probably type it out long form, actually type the word square root. But as a shorthand, we can use SQRT. So we've got 10 times the square root of, inside parentheses, x plus 8. We're asking it to find that derivative for us. So again, we want to check what the input is here. Wolfram Alpha is using this d over dx notation, which is another type of notation to represent the derivative. So we're taking the derivative of this function, which looks like what we want it to look like, and we get a result of 5 over the square root of x plus 8. So again, I can just click on this output to bring that result into our entry box here, which saves me, again, the trouble of just having to rewrite 5 divided by the square root of x plus 8. And I can say, again, evaluate this function for x equals 4. And we get that result of 5 over 2 times the square root of 3, or we get an alternate form of 5 times the square root of 6. So these two results are exactly identical to each other. All that's happened from one to the other is that in this case, this is with an irrational denominator, since we have that square root in the denominator. Multiplying that by root 3 over root 3 would yield 5 root 3 over 6. So this version, this alternate form, is that exact same answer but with a rationalized denominator. So in example 2, we get the derivative to be 5 over root x plus 8. We get our result of evaluating the derivative at x equals 4 to be 5 times root 3 over 6. Whether you use this answer or the answer with the radical in the denominator doesn't matter to me. They're both equivalent answers. So 5 over root 13, or 5 times root 13 over 13 is what we'll get if we evaluate that at x equals 5. And evaluating at x equals 7 should give us root 15 over 3. So again, in each of those examples, what I've provided is that alternate form where the denominator has been rationalized, but both of these answers are accurate answers. So in part C, just looking at one more example here, we want to find the, or in example 3, we want to find the derivative of 3 divided by x plus 2. So a lot of using Wolfram alpha just comes down to knowing kind of the format to type in these functions. In this case, we want to make sure that that x plus 2 is inside parentheses, like I have it here. If we didn't have those parentheses, Wolfram alpha would interpret it as 3 divided by x, that fraction on its own, and then it would add 2 to that. So we just want to make sure we get those parentheses around the denominator. And then verify that, again, our function looks correct here. So we get a derivative of negative 3 over x plus 2 squared. So h prime of x will be negative 3 over the quantity x plus 2 squared. Evaluating that function at 4 would give us negative 1/12. But what we do want to look at is look at what happens when we evaluate that function at x equals negative 2. So hopefully we can quickly see in the denominator, if we plug in negative 2, we would get negative 2 plus 2 gives us 0 squared. So we would get an undefined result. So let's see what that output looks like in Wolfram alpha. So we want to evaluate this function at x equals negative 2. So Wolfram alpha gives us this infinity with that squiggly tilde sign over the top of it. It gives us some information about the limit from the left, the limit from the right. What we could see if we were to look at the just plotting this function, so this isn't looking at the original function, it's looking at our derivative function. We can see that what we have occurring at negative 2 is a vertical asymptote. So that information it was giving us about the limit from the left, limit from the right approaching negative infinity was some additional information about the behavior of the graph. But in short, for the question that we're being asked right here, evaluating h of negative 2 is an undefined result. We can't evaluate this function at negative 2 because we get that 0 in the denominator.